So a little bit of background on Jim, as I say, he's called himself a VHDL Evangelist, and the title of his talk is going to be OSVVM Leading Edge Verification for the VHDL Community. Jim is an innovator and leader in the VHDL community. He has 30 plus years of design and teaching experience. He is the chair of the IEEE 1076 VHDL Standards Working Group. He is co-founder of the open source VHDL verification methodology. That's OSVVM, the subject of the talk today. And he's the chief scientist of the packages and methodology. He's an expert VHDL trainer for SynthWorks Design Incorporated. In his design practices, he has created designs for print servers, IMAE1T1 networks, fighter jets, video phones, and spacecraft. So a very diverse set of designs. Whether teaching, developing OSVVM, consulting on VHDL design and verification projects, or working on the IEEE VHDL standard, Jim brings a deep understanding of VHDL to architect solutions that solve difficult problems in simple ways. He's located in the US. I believe he's on the West Coast as well, so it's a very early start for him. So again, thank you very much.
Well, thanks to Mike and company for inviting me here to talk about OSVVM. It's one of my favorite things to talk about. And there we go. So I have a whole list of things about OSVVM to talk about, but the first thing I'm going to talk to you about is VHDL and its relationship in the FPGA market. And then we'll get into all the aspects of OSVVM. So as Mike mentioned, I have a substantial background, including about 30 years of VHDL. And, you know, it's this expertise that I bring to OSVVM that really makes it one of the best VHDL methodologies out there. All right. So where is VHDL as far as everything else goes? Because, you know, of course, there's rumors in the industry that, you know, VHDL was dying or something of that nature. That's nonsense. VHDL is #1 in the FPGA design and verification market. This comes from the Siemens-sponsored Wilson Research Group 2020 Functional Verification Survey. We can see that worldwide, 64% of designers use VHDL. In Europe, it's even more. And worldwide, 50% use OSVVM for verification, or use FPGA verification, VHDL, and 72% of that is in Europe, 72% in Europe. So while Europe brings everybody up, keep in mind that Asia trends towards Verilog, system Verilog, so it also brings those numbers down. So I expect these numbers worldwide to probably represent what's going on in the US, or be fairly close. From a verification library sense, worldwide, 18% use OSVVM, or if we translate that to just VHDL, that's 36% use VHDL in the FPGA space. In Europe, 34% use OSVVM, and only 26% use system Verilog and UVM. So next time your vendor comes to you knocking on the door saying, hey, you should switch to system Verilog, what they're trying to do is make that 26% number go up. But there's certainly not, you know, if we look at the FPGA space, there's certainly not more system Verilog engineers out there than even OSVVM engineers, again, in the FPGA space. So we asked the question, what is OSVVM? And I had to come back to this recently because really it's been growing. And so what is OSVVM? It's a verification framework. It's a verification utility library that includes leading edge verification things such as constrained random, functional coverage, scoreboards, error handling, message filtering. And then we're a verification component library that's growing in components. And we're a script library that aims to write scripts in a tool independent manner and also try to write them as simple as possible. So while it's based on top of TICL, we try to make it so that at the user level, we're not writing TCL. Okay. So benefits, we simplify test case and verification components. We bring a high degree of readability, which I'll hopefully demonstrate in this presentation. And my goal is that it's not just readable, it's reviewable by all, meaning not just verification engineers, but also hardware engineers, and also anybody that programs. So your software and system engineers should be able to read your tests, understand what you're doing, and hopefully give you feedback. Oh no, that's not how we're using it. So because when I go into the lab, I want to have a high degree of confidence that the way I've tested it is exactly how the software team intends to use it. We have powerful reporting, and part of that is HTML for humans to read, but we also have JUnit XML for the continuous integration tools to read. Okay. We've created features that work just like built-in language features. And OSVVM can be added incrementally to your design, so you don't have to just switch over to the whole thing. You can incrementally add it to your current VHDL test bench and models. We have a long history with the roots of OSVVM. It really started in our training classes and continues in our training classes. So we started with our transaction framework around 26. We added randomization and scoreboards and memory packages. It wasn't until 2010 that we added the functional coverage capability, and then we've just grown from there. Okay. Taking a look at the framework, again, this has the roots all the way back to 97. Actually, I started using it prior to that on some consulting assignments. So the OSVVM framework looks identical to the System Verilog framework. We have verification components that implement interface signaling. Our test cases are in our sequencer, which is called test control. And then our test cases are in separate architectures of test control. Okay, so we're taking advantage of VHDL's capability of separating the entity and architecture here. At the top level, the framework is just a netlist. Yeah, some might call this a test harness, but it's just instancing the dot, instancing the verification components, instancing the test controller, and this is just like RTL design. So it's nothing outside of the wheelhouse of an ordinary RTL designer. And we'll see that as we go down through the levels hierarchy. It's nothing outside of the wheelhouse of an RTL designer. All right. So starting with the transaction interface and transaction API. So that's the interface is the record. On the left, we have transaction subprograms. That's the API. And we add to that the verification components. We add to that the test sequencer. So when we talk about the framework, these are all the elements of the framework. All right. The interface is just a record. Okay, so there's nothing fancy here other than perhaps the types, and we'll get to that in a second. So we have some fields dedicated to handshaking, and then the rest of the information in the record is dedicated to transaction handling. So the fancy part is the record port is in-out. So each element here has to be a resolved type, and we've defined those resolved types in OSVVM's resolution package. Okay, and this supports all of VHDL's comment types. So beyond just standard logic vector, we can put integers, time, and that sort of thing into our interface record here. Okay, our long-term plan is to migrate to VHDL 2019 interfaces, but VHDL 2019 interfaces are a layer on top of records. So it's a very, very minimal change. The only thing we have to do is add a view declaration for our record. Okay, so our transaction initiation API is just a set of procedures that do things, that cause things to be done on the interface of the verification component. So really, these are very simple. the only thing they have to do is put information into the record, this stuff from the calling parameters, handshake with the model. This is basically saying, hey, verification component, I have some stuff for you. Will you do it, please? Okay. And then when it finishes, if we're running a blocking transaction, we grab the results. But keep in mind, we also have non-blocking transactions that just dispatch and run and run from that point and complete immediately. All right. And all that is up to the discretion of the verification component as to what its objectives are and what it needs to implement. So if we look at, if we consider now our transaction interface and transaction API, one of the observations I came to some years ago is that some interfaces do the same thing. Okay, we have address bus interfaces like Axie, Avalon, Wishbone, and they all do reads, writes, maybe some of them do bursts and that sort of thing. Likewise, we have streaming interfaces, and whether it's Axie Stream or whether it's UART, they're really doing the same thing on the interface. They're doing sends and gets. Okay. So what we did then is we built our own little internal standards that we call our model independent transactions. And this first one is our address bus model independent transactions. And in that, it's basically a package, right? And we define our record and we define our transactions that we're going to support. And this here is a subset of those transactions. Then we have our stream model independent transactions, same sort of thing. We define our interface and then we define our transaction. So when we add that view for 2019, it'll be added into here. Yeah, and we've already prototyped that. So Aldec has already implemented a good portion of VHDL 2019. So we've already been testing with their stuff and we're ready to go. So again, we support numerous additional transactions. This is just a subset of them. And that includes things like bursting on our interfaces. And we handle that very efficiently because we're handing off information to the interface, but it's kind of interesting because we're using singleton data structures and we're able to pass things like FIFOs through our interfaces, or at least references to them. Our verification components, it's nothing more than you have the DUT interface, which in this case we've abstracted away with a record, which was a very interesting project in itself, because if you recall, VHDL 2008 adds unconstrained elements to records, and we're using that here, and that caused all kinds of grief until we got all the tools working on that aspect. And then we have our transaction interface, okay, our address bus rec type. Okay, so inside the verification component, a very basic blocking sort of verification component. The only thing it needs to do is call wait for transaction. Okay, and wait for transaction is the partner to request transaction. So when request transaction says, hey, I got something for you, wait for transaction wakes up. And then it drops down and decodes that transaction. Then it might call subprograms at this level, or we might write code at this level. My preference is to write code because at some point in time, if you continue an abstraction chain and abstract too much, then you reduce your readability. Okay, so you really have to decide where is the point that we need to show or illuminate what our design is doing. All right. Now, here we're benefiting from the OSVVM model independent transactions because if we didn't define the interface and the transaction API, we would have to be writing that. But since with model independent transactions, you don't have to do that. So we're just focused really on writing the verification component. And you can see the verification component is simple enough. And, you know, there's aspects of it that can be very RTL-like if you like. So it doesn't take a verification specialist to write this. All right, then we have our test sequencer, and its interface contains primarily records. The entity interface is in one file. The architectures are in separate files. So the only time I separate these is when we have multiple architectures of a given entity that are going to be live at the same time. So for RTL, I don't do it. Just really for this application here with a test sequencer. All right, so let's take a peek into the test sequencer then. What we have then is we have the whole test in one file. So it's reviewable. You can see everything here. We have our control process. And so that's the first thing we're going to see. And this is responsible for initializing and finalizing our test. Then we have basically one process per interface that we're talking to. This gives us concurrency, just like your design. Concurrency, mind you, is just independent operation. And in these processes, we call transactions procedures, okay, to build up what we're doing. And it makes it easy to write directed tests, to add things like functional coverage, but also to do constrained random tests. And we're gonna explore all of this in today. Now, sometimes when you're writing in this concurrent environment, we're going to need synchronization. So we kind of borrowed a synchronization method from software called barrier synchronization. And that basically says when both processes have arrived at this point, then we'll release and do the next set of stuff. So that allows some very explicit synchronization things. You'll see we're using that here for the start, and we're also using that for our completion here. But depending on the test, we may use it more than this. Okay. And then we have some very powerful error reporting and messaging. The only thing we're seeing here is our end of test reports that we use to finalize our tests. And this is an essential part of our report creation. Okay. And again, you'll note that this is simplified by the OSVVM model independent transactions, because when we're calling those procedures, they're defined by the transaction API and the model independent transactions. So if you have two address bus verification components, they're going to be implementing a subset, perhaps, of the transaction API defined in the address bus model independent transactions. So they'll have the same format, they'll have the same name, and all of that. So in addition, if you wrote any wrappers that combine a set of things together that make sense for different interfaces, you can reuse them because they're the same thing. Okay. Okay, so in initialization, the first thing we're going to do is set up the test name, and we do that with set alert log name. Generally, I make the file name, the test architecture file name, match this name. It makes the OSVVM flow quite a bit easier. And often this name also matches, we have a configuration for this, and often we'll have the configuration name match this name too. So one of the features of OSVVM is we have transcript files. A transcript file is we're able to log all to one common file, our VHDL output. Now, simulators, of course, have a transcript, which if you were writing just the output, you could have it there, but then it's intermingled among a bunch of other stuff that you may or may not want it intermingled between. We can do that too, because we can redirect it to a file, but we can also turn on our mirroring mode, which causes the output to be written to a file. All right. With our messaging, we have IDs. IDs identify who's generating the message, and we get the IDs by calling new ID. Okay. We can turn messaging on and off. Most of the messaging is off by default, and then here in our test case generation, we turn it on. Okay. Oops. And then at the end, we're coming down to the middle of this process now, and we call wait for barrier test done, and we say 5 milliseconds, and the 5 milliseconds here is a timeout. Okay, so we're saying, hey, now let the rest of the test run, and wait until it's done. All right. You'll note that new ID here is an overloaded constructor for OSVVM singleton data structures. Right now, we're calling it from within the processes. We're making a small adjustment to the language that will allow us to do it in a declaration also. Right now, vendor support, most vendors allow you to do it in a declaration anyway, although technically doing that is illegal, so I'm at least never going to show it in my presentations and not going to have it done that way in any of the released OSVVM verification components. Okay, we'll do it the harder way until the language says it's legal, because OSVVM is intended to be strictly VHDL legal. Okay, so self-checking. So, and that's an important part of our test. So we're writing a directed test here. We're sending, we're getting, and all that kind of stuff. So when we get, we know what we sent. In this case, we're kind of keeping everything aligned. So we can call this affirm if equal. This is our checker. And it basically says, if they're equal, then say passed. If they failed, then say error. Okay, and that's reflected down here. We're also using ID. You can see we called it with TBID that we set up in the control process, and it tells us where it came from. So it says down below, error in TB. Okay, so it gives us the context of what we're doing. We can also move these checkers to the verification component simply by, instead of calling get, we call check. Okay, so we're handing the expected value off to the verification component. It's then doing the check. So now we see in the report, we see the verification component's ID being used. Loggers are all about messaging. We have log always that always prints, and then we have other levels, debug, info, final, and past. These are all individually and separately enableable. There's no level precedence between any of these at all. But they're also controlled by ID. So we can turn things on and off for a specific verification component. And this is, especially in this scenario we're talking about here, we have a UART in play, right? So it's very relevant because maybe I'm debugging UART and I turn on the UART's info flag, but I want to be careful not to turn on the address bus verification component's info flag, because if I do, it's generating a huge amount of information in the amount of time that a UART generates one. So if we had them both on, the UART information would be lost. Okay, so above, debug's not on, so the only thing we're going to see is the always message that is printing first. Okay. Okay, so next we're going to add randomization to our testing. And you might be sitting there saying, why do I want to randomize? So if I look at a directed test of a FIFO, and I'm tracking the FIFO word count here, and I'm tracking it, looking at it, interestingly enough, as an analog signal. Okay, and by doing that, I can get some subjective feel to what's going on in the test. You can see on that first ramp up, I'm filling up the FIFO. On the ramp down, I'm emptying the FIFO. And then you can't really see it there, but I have two words in the FIFO for a long period of time, and I'm sending and receiving at the same time. And then down here, at the end here, I'm doing some read empty tests, and I can see that because I also am tracking, I have some coverage here that's tracking the number of read empties I'm getting, and then I fill it up and I'm doing some full testing. So I'm seeing that when I try to write one more word after it's already full, that it's successfully held off. And certainly if I looked at the verification plan, I could have a check mark in every box there in my verification plan. But then you might be asked, is it fully tested? And we might think so, but if you've done engineering long enough, you realize that when you move like a robot like this, life brings you unexpected things and things can break. So what we can do with constrained random then is we can set up some heuristics about filling and emptying and run the FIFO through its paces, hit our endpoints, because you can see we're still monitoring those here, and hit our endpoints and get really decent job of coverage here. All right. Okay, so the key point about this then is we're generating realistic stimulus in a timely fashion. When I say timely, I mean to write. Okay, I don't necessarily mean running. Constrained random does have some overhead, and it may take longer if you had an equivalent test that was running in directed testing. Maybe it would run faster. Okay, but this sort of randomization is ideal for when we have a large variety of similar things, so modes, sequences, network packets, and processor instructions. And you might note that a lot of the early constrained random stuff was driven by people in networking. That was what was going really active at the time that it was developing. All right, so what does OSVVM have in related to randomization? Well, we have a very simple random toolbox, okay? So we can randomize a range, min and max. We can randomize a range like 0 to 15 with an exclude set. We use integer vectors as a set, so that extra set of parentheses in there, it makes that a single parameter, okay? So it says do everything except for 5 and 11. We can do sets. Again, we use integer vectors to represent sets, and we have a set of exclude things. In this case, the exclude things are typically not static like this, but instead dynamic. Exclude the last two values, or the last value and the fifth value from the last value for some reason. All right. We can also do weighted randomization, and weighted randomization here is going to generate a set of numbers. And when we give it a static value like this is an integer vector, it's going to give us the values that correspond to the indices. And in VHDL, we number the indices for integer vector anyway, 0 to n minus 1, where the leftmost value is 0. And then we have n vector elements in there. There's 3 this time, so it's 0 to 2. All right. And what this says then is these weights say, we individually, we don't know what it means. But when we sum them up, then we know, oh, the first one's 7 out of 10, or 70% of the time it's going to happen. The second one, 20% of the time is going to happen, and so on. Okay, finally, we can do weighted randomization where we get the value and the weight. All right. By itself, this is not constrained random. Okay, by itself, this is not constrained random. It really takes wrapping this with some code to make it constrained random. So let's see what we can do. We're using the weighted distribution here. Generally, I make these things add up to 10, 100, or 1,000, or 10,000, something of that nature. So the 70 here is going to be 70% of the time. So I'm doing a randomization where 70% of the time, it's going to generate me this first case. And for the UART, this first case might be don't inject any errors and generate me a normal set of numbers. Okay. And then we have parity error. The interesting one is stop error. Remember, we said it's constrained random. One of the funny business that goes on with stop errors, and this actually happened to me, is what happens if you inject a stop error, have even parity, and randomize the 0 as the number that you were going to generate? Well, the interesting thing then is a 0 with 0 parity and 0 stop bit is a break error. Okay, so you get detected as something else. So we can't generate a 0 here. That will get generated when we generate break errors, because we're going to do those too. Okay, and then we do our transaction. Now, doing our transaction here isn't a requirement. We could have done it up in the code. We could have done multiple transactions up in the code too. So it just depends on the style and what our target is. Okay, so again, constrained random in VHDL is randomization, toolbox, plus code, plus transaction calls. Okay, and it's all right here. Wander through the code, you can see what it's doing. Okay. Most of it's pretty simple. Now, what about checking? Well, I could repeat that pattern in the checker process, but that's tedious, error prone, and in my mind, not a viable methodology. So we're not going to do that. Instead, this is a great time to introduce OSVVM's generic scoreboards, because we're going to use this as part of our solution. Okay, so scoreboards are a data structure that are intended to help check data when it's minimally transformed, like it just went across a network. Okay, like we send a UART word in to our DUT and then retrieve it on a different interface. Okay, maybe we're using one of the address bus interfaces to get it and check it. Okay. Okay, and then we'll say push in one side and check on the other side. And we'll see that in a minute here in the code. So OSVVM's generic scoreboards have FIFOs plus methods that allow it to be a scoreboard. It handles small data transformations. It handles out of order execution. It handles drop values. Okay, this is something that originated in 2006. So we were on the leading edge of the curve of having generic scoreboards. I don't think generic scoreboards came along until a little bit later because it took, it was a 2008 feature. It was part of Accelera 2006, but it was a 2008 IEEE feature, and it took vendors some time to get everything working right. So we parameterize it with generics on the interface. Okay, pretty much supported by most vendors at this point. And then we have the API. Okay, now the API here is a singleton API. Historically, we had you interact with protected types. As of summer 2021, we changed that. Okay, so we changed to basically all of our data structures are singletons now. Okay, and what's different is the use model. You no longer have to work with some foreign-looking interface. So in our library, we have scoreboards for standard logic vector. We have scoreboards for integer, meta match, 2HX string come from the OSVVM library. We needed a special match because in verification, in some of our verification components in particular, a U needs to match a U and not be false. Okay, and X needs to match an X and that kind of thing. And 2HX string, 2H string, if you get a U, it prints it as an X. Okay, and it doesn't differentiate between 4 U's and mixed values. So 2HX string does. If you get 4 of the same standard logic character in a row, it's going to print that. Okay, so except for H and L, it's going to print those as 0 and 1. Okay, and if it gets a mixture of things, it's going to print a question mark, and then in parentheses, it's also going to print a binary value to string. All right. Okay, so scoreboarding. This is what it's all about. So step 1, we create an object for the scoreboard. Right now it's a signal, and then we call new ID, and this was in the control process. I just didn't talk about it there. So this is new ID. Again, it's used with all our singletons to get the ID. Each ID type is unique, so we don't have a problem with the overloading and using the same names. So it made something, again, I promised, one of the things I promised or claimed was that we're headed for something that works just like built-in language features. So once we get this to be allowed to be initialized in the declaration, it will look just like a first-class data object. And that's the beautiful thing about singletons. And then down in our code, before we send a transaction, we push the information in the scoreboard. And then when we receive a transaction, we do a get to receive the transaction, and then we call check in the scoreboard. Okay, so the big deal is in the TX process, always push before we send. The reason that's important is because we're not checking for the scoreboard to be empty or not, and then doing the checking when it's not empty. We're using the transaction as our handshaking. So by putting it in before we start and by receiving the transaction, we know we can check the information and it's in the scoreboard already. Okay, and for a UART, you've got to watch out for that, because a UART receiver actually center samples and will finish a half of a baud period ahead of the transmitter. Okay, the next thing, once we start randomizing, we need to consider having functional coverage, because with randomization code, how else are we going to tell what is being done? Okay, so what is functional coverage? It's simply code that tracks items in our test plan. So it's going to be requirements, features, and boundary conditions of our design that aren't illuminated already by code coverage. We want to track them with functional coverage. Okay, so again, with randomization, how do we know it's done? Our done metric then is going to be 100% functional coverage and 100% code coverage. Code coverage we might have exceptions for, like with the when others clause. Okay, so item coverage. So item coverage is all about tracking relationships within a single object. So code coverage can tell you an object has been written to or not, but it certainly cannot bin the values in that object. So if we're looking at a DMA controller like thing that supported transfers up to 255 words, we're going to look for small transfers like 1, 2, 3, and individually track those to see that they happened. And we're going to look for big transfers 253, 254, 255, at least big relative to this interface. Okay, and then the things in the middle, we're going to kind of aggregate together, maybe in 2 bins, maybe more if you need to, maybe 4 bins or something of that nature. But we're really worried about the endpoints because that's where things tend to break. Okay, cross coverage. We want to be able to track relationships between independent objects. Okay, so we have an ALU. We want to know that for each, for input 1, that each possible selection of registers that can be routed to that have been routed to it and used with each possible selection from input 2. Okay, and that's not something that's in the code, and that's something that's never going to be in the code. Okay, so why not code coverage? Because it can't bin, it can't do cross coverage. Code coverage simply tracks execution of the code. Another thing code coverage can't track, your current design has 2 programmable counter timers in it that are generating interrupts for your CPU in it. Your new design requires a 3rd. You forget to add it. Your code coverage isn't going to tell you that. But your test plan is going to say, I'm expecting this interrupt line to be set, and it's being set by the 3rd programmable timer counter, and I should be seeing that. If I'm not, then something's missing. Okay. All right. So what we do for our coverage is we use coverage package. Okay. So it simplifies our definition, collection, and reporting. It has a data structure internally, along with some internal configuration parameters. We have an API to all the coverage features. It's in a singleton, and with, I think past October of 2021. So in the release, the October release, we started adding our coverage reporting, not through write bins, but through end of test reports that produces an HTML coverage report. And that's an important step because that gives us the ability to match what System Verilog does as far as coverage reporting goes. And I'll show you that at the end. Okay. So functional coverage is easy. Okay. So collecting functional coverage is easy. What we're looking to do here then in our UART is we're looking to track what's happening in our status word. So we're looking for these bits to be set, and we're going to track these as integer values. All right. So to write functional coverage in OSVVM, we have our coverage object. We call our new ID to initialize our data structure. So just like scoreboards, just like everything else, it's new ID, typically a name. Here, we're correlating it with some ID. Okay, some alert log ID. All right. And then we're collecting our coverage. So we call genbin1. This is the value I'm tracking from the previous slide, the integer values. And I'm calling adbin. So genbin is kind of a pre-formatter for adbins. It really wouldn't be necessary with adbins to do that, but it simplifies and makes the use model consistent with add cross where we do need it. Okay, we collect our coverage, okay, with iCover. So we're actually monitoring things. So we did a get, we do a check, and we record our coverage on what we just saw. Okay, so we're at the receiver side. This is the place typically that coverage is collected. All right, so one of the things we note here is that functional coverage with OSVVM is just as concise as with language syntax. All right, so intelligent coverage. So let's add another, on the test generation side, let's add some more randomization coverage or randomization capability. So this is going to randomize using functional coverage holes. We're doing the same thing. We create our ID, we create we do call new, and then we're going to add some additional things in here. The first thing is a name. That's not required. That's an optional thing, but it's a good practice to do. And then we add our coverage goals. So this is our coverage goals here. Okay. And then we're just randomizing. So to randomize in the coverage model, we call getRandPoint. For if it's item coverage, we get an integer value back. If it's cross coverage, we get a integer vector back. So, and we're using basically the same target values we did with the constrained random, except the same target actions that we used with the constrained random, except the numbers changed. So it's not 0, 1, 2, 3. It's the numbers matching what we put into the coverage model, the 1, 3, 5, 7, and then 9 to 15. Okay, and then we're collecting coverage here. Now, one big thing about collecting coverage at this point, generally we want coverage collected at an observation point. So to collect coverage here, we have to already have verified that our send operation here actually cannot do anything other than send the operation. Okay, so we have to have already verified that send does exactly what we tell it. Otherwise, we'd have to move this iCover to somewhere else. Maybe we could have used the one on the receiver side, right? So that would have been an appropriate thing to do. In fact, we could have merged the coverage models here. I just didn't, because when people are just getting started, that just makes more places for things to go wrong when things are shared. Okay, so we could also call this intelligent coverage randomization, coverage-driven randomization, where here the coverage goals are used as randomization weights. All right. We also have, in OSVVM, we have protocol and parameter checks. We use the affirm and affirm if. For self-checking, we use alert for error checking. So here, alert if, well, if we ever see in a memory, if we ever, and this is a very old memory, mind you, if we ever see chip enable, write enable, and output enable active at the same time, something bad just happened. Okay. Parameter checks in the OSVVM package if max is less than or equal to min. We also have alerts. We can turn them on and off. Note, even if you turn things off, you'll see later in our HTML alert report, we still report them. So you're still going to know about them. It's going to be very hard to ignore anything that's disabled with OSVVM. In fact, by default, they also still count as errors. You've got to turn that off too. And in our quick reference and our user guides, we show you how to do that. We can also stop a simulation. So generally, if you just get an error level operation or alert, we don't stop. We continue going. But this one says stop after getting 20 errors. We also have a failure level that will cause the simulation to stop immediately. Okay. Then a warning level that doesn't stop either. So we've seen a whole test with a number of different test generation methods. Now we're at the test finalization. We're waiting for the test to be done. All of our tests, other tests got done. So we complete, we check. Is now the current simulation time, that's a function call in VHDL, is it greater than or equal to 5 milliseconds? Because if it is, we timed out. And if the test did nothing, say it catastrophically failed without signaling an error, we're going to inject an error just because of the timeout here. We might require that our scoreboards end empty, so we can check that. We might require that there was some self-checking in our design. We can get, so that's one of the advantages using the affirm if for self-checking, is that we count them. Okay, and if you didn't get any checks, then it wouldn't be appropriate to say test pass now, would it? We can also do some file checks for you. So affirm if they're not different. So in other words, if the files are equal, then test passed. Okay. And then we do our end of test reports. Okay. So taking a look at what that does, when you call end of test reports, historically, this is what all we did. So we produced this report. If it passed, we gave you a nice pass message and told you all at, we got affirmation that passed are 48 and number that checked are 48. That gives us a correlation that everything went right. Otherwise, if it failed, we give a complete listing of all the IDs in use and try to identify who failed and why. Okay, is part of it. Okay, so all right, so we're going to transition now from our test case to our scripting. OSVVM scripting tries to make scripting simple. Yes, it's Tickle, but no, you shouldn't have to write any Tickle, okay? Tickle is only there when you need it. So generally, even in OSVVM, when we're writing things to build OSVVM, the only thing we use of Tickle is an if statement. And that's only really just because we want to check, do you have this submodule? And if you do, let's build it, okay? And that's the only fancy stuff we're doing. Or sometimes in our OSVVM scripts, if it's vendor ABC, then do this, okay? All right, so it's meant to read just like a text file, but it's Tickle. It works in GHDL, Aldeck tools, Siemens tools, Synopsys VCS, and Cadence Excellium. So we have really good vendor support, and that's because I've personally collaborated with them and made sure things are going well. It remembers settings like library, like code coverage enabled, and language revision. So yeah, one of the things we do is we make code coverage easy, because what we're really aiming to do is run a suite of tests, collect code coverage on each test, and then merge it. That happens automatically because you ran a build, and give you the results at the end, okay? So that you don't have to do all the monkey business of merging things and all that kind of stuff. Note, all the paths in this file are relative to where the script file is located. Okay, so that's one of the monkey business that I don't like about Tickle, pure Tickle, is that when you do a do or a source in Tickle, then the file has to derive where am I running from, because if you're running simulation scripts, they have to run from the directory the simulator's in. So if they're not in that same directory, there's a lot of monkey business going on. And I just don't like that, and I don't think the user should have to be exposed to that level of complexity. So OSVVM takes care of that in all of the OSVVM commands: analyze, simulate, build, include. They're all relative paths. Okay, so we do at the top level when we're running scripts, we use build instead of source or instead of do. And inside of our procedures, we use include. Okay, build creates a outer layer of infrastructure in that, in a reporting structure is what it does. Yeah, so you only want to use build in one place in your scripting. Typically, I use it at the top level. Okay, by calling build, let me sneak the actual report here. It's an HTML report. So this is my build summary report. So when you call OSVVM and run a test suite via OSVVM scripts, okay, and you called end of test reports, you get this, interesting. You get this first build status. We see passed, we see the number of tests that pass and so on. And you can see we've got, we can see what we're going. And if you have coverage enabled, you can click on this link and go see coverage. We're gonna skip over that. We have our test suite summary here. Okay, so we have our test suite summary that for each test suite that ran, and you can see I ran 5 of them here to run the OSVVM basic verification component regressions. And you can see we're reporting number passed, number of failed, skipped. If you have requirements in design, none of these do, then it's going to report on those. And reporting disabled alerts. We want that to be 0, right? Yeah, okay, because we don't want to accidentally, turn some alerts off for some part of the test, but forget to turn it back on when we're going to the final phase. So we track it here so that you can catch yourself on that and gracefully recover. We report everything, and we even record the functional coverage here. So this test turned on coverage. Also, though, and I'm going to go through the next slide this way too, is you can click. So that was a link. Let me open it up, separate tab. You can click down into our, for each test case, we have a detailed report where we have the alert report, which is down in this file, the functional coverage reports, and the scoreboard reports. They're all in this file. And by the way, this is all automatic. End of test reports. That's all you got to do, because the functional coverage, the scoreboards are in singletons. We can iterate that data structure and find them all and report them all. Okay, so that's all in this file. We can see the Alert report starts with the settings. Any place you see a triangle, you can close that stuff. And then we have all the alerts, all the alert counts. If we scroll over, we can see we also track all of the disabled alert counts. Okay, so we can track exactly what's happening. We have our functional coverage reports in here. And then down at the bottom, we have our scoreboard reports here. I could have clicked the link up top. We also, so for our transcript files, this is the VHDL transcript that we created here. So anytime you do a transcript open, we remember that. We put a link to it in our reports. We can also link to our simulation results. So basically everything you run in VHDL, this is your simulator transcript now, okay? We have everything. When I clicked on that link, I jumped into the part of the test that was for this test case. So it automatically opened this one up and shows me what's going on in there. Okay, and all the results. You can see I had mirroring on here. Generally, I turn mirroring off when I'm running regression, so it's kind of interesting that it was on here. And I can quickly find if there was a bug in a test. This is part of helping me debug. And if you look at, again, go back to the surveys. Yeah, that was everything. If you go back to the surveys that like Wilson verification survey, you'll see that debug takes like 48% of a verification engineer's time. So it's huge. It's huge. So running tests and debugging. So have set things up to help you debug them and make it easier so that when you have changes in OSVVM, when we have pull requests, this stuff is infinitely useful to us. Okay, this is just showing the stuff I talked about on the other stuff. So, okay, so how do I get it? So OSVVM documentation starts at GitHub. So we have everything on GitHub, and our documentation we have as HTML, osvvm.github.io. There is also a PDF repository of all the stuff. So right now we only have the top level documentation as HTML, everything else is PDF, but in this we have links to everything, all the documentation stuff. We also have a documentation repository. The README file for that is still undergoing updates, and with this month's release, that's been one of the focuses, is getting the documentation up to date. And one of the things Mike asked me was, how does a college student get started with this? So that was one of my this is going to be one of my answers to that. Is we have now extensive documentation on all aspects of OSVVM. So again, how do I get it? Well, if you know how to use Git, you can Git clone it. It has submodules, so you do have to do it recursively. Or if you hate Git, there's a zip file at osvvm.org/downloads. The cost there is you do have to subscribe to osvvm.org. We run our scripts. I typically run them from a sim directory. That way, if your simulator litters, I can just get rid of the sim directory. So if I were in the same directory right now as OSVVM libraries is in, that contains OSVVM libraries, I could in Tickle say file make dir sim, so create a sim directory in my simulator, CD to it, and then source the OSVVM startup. So this is how we start Siemens tools and ALDEC tools. There's one extra step for Active HDL. The documentation will walk you through how to start the other tools, though, because it's a little bit different. So running VCS, GHDL, and Excellium is slightly different. Okay, but it's all in our scripts there. Okay. All right. So to build everything, we just say build, and then assuming we're in the sim directory, ..osvvm libraries, osvvmlibraries.pro. And then to run some of our tests, we've got these run all tests.pro. .pro it's a procedure layer on top of Tickle, so the .pro is indicating you need to have run the OSVVM procedure layer. Okay, so it's indicating dependencies on that. So there's a run all test basically for every verification component and the top level in OSVVM libraries. There's also a run demo tests, And also, and there's a run demo test with coverage. And if you're going to run one, that's a pretty good one to run. If you've got one of Siemens tools or one of Aldex tools, with that test, you'll get the coverage reports, which is kind of really exciting, at least for me to see. Wrapping up then, all you need is OSVVM. We've got all the utilities, everything. We're not integrating things from any outside source. We've got a verification framework. We've got our utility library. We've got our verification component library and our script library. So you can upgrade, this is a big deal, you can upgrade your current VHDL approach incrementally. We've created an environment that allows verification to be done by either a design or a verification engineer, meaning you can consider your engineers, your VHDL engineers, as non-specialized resources and have them rotate their responsibilities. Tests are reviewable and readable by all. Again, I want to get the software and system engineering team involved. I don't like debugging in the lab. If they tell me, hey, what about this test, and it's something I missed, I'd rather write it in the simulator and test it there than find it in the lab, right? It's powerful and concise. And we really, as far as conciseness and capability, we rival other verification languages like System Verilog. Okay, so System Verilog is not the only answer. In fact, OSVVM gives you all of these features on an ordinary VHDL 2008 simulator. Okay, so you're not paying incremental licensing fees like you will with System Verilog. And we support mixed approaches, very straightforward in our test cases. So we're not specializing constrained random. We can write directed, algorithmic, file-based, constrained random, and the last one, intelligent coverage randomization, which is a lightweight, low-end capability of intelligent test benches. And if you followed intelligent test benches, Accelera made a standard. They started out calling it intelligent test benches, but then they went to, what did they call it? I lost the word. It'll come back to me later today, but I'm sorry about that. All right. Appreciate you all coming, and I'm ready for questions anytime.
Thank you, Jim. Michael asked the questions for us.
Hi, Sarah. Can you hear me okay?
Yes, we can.
Absolutely.
Thanks.
Okay. Well, thanks, Jim. Very timely and a very comprehensive overview of OSVVM. So let me, there's a few questions. Hopefully they'll fill up the 5 minutes. There's a couple of questions from Alexandru Dinu. I think he's asking whether this effectively can be done on an FPGA as well as in simulation.
On the hardware platform itself, that's
Yeah.
not something yet I've explored. So.
Okay. Yeah. Okay.
So saying another way, our verification components currently are not synthesizable, and we're using that record interface that's using resolution functions. So until we have the VHDL 2019 interfaces and the synthesis vendors have implemented that, yeah.
Okay, so at the moment it's non-synthesizable. Okay.
Yeah.
So one question for myself as well. You seem to have gone out of your way to make this easy for designers as well as verification engineers. I'm not sure the UVM has done that to the extent it's been done here. Do you find bigger take up with designers than you would with SVUVM?
I would expect there to be, but the big thing that I see in some of my training customers who use System Verilog but do VHDL is, they've got a limited staff of verification engineers, and when a new project spins up, they have all the VHDL people they need, but the System Verilog people, to keep them all busy full time, are a limited resource, And as a result, they're not always available when they need them.
Okay.
Okay. So that's the importance of being able to juggle people as need be. And if you remember back in the early days, when we got a new person, we always threw them into the verification environment first. Okay. And that actually turns out to be, from a test case writing standpoint, when we're using the model independent transactions, that's a good way for them to learn what the design does, by writing test cases for it, by reviewing it and writing test cases for it, so they can learn our product, and then they can go and help write the next generations of it.
Okay, thank you. There's a couple of questions from Tian Bale. So and this may be a big answer, but maybe you could try and summarize it for us. Is there any advantage? What's the main difference between OSVVM and UVM, would you say?
I'm not a UVM user, so I really can't take that on.
Okay.
Yeah. Obviously,
Okay.
I've invested all my time in VHDL, because in my mind, let me answer one aspect of that. In OSVVM, we're writing verification components and entities and architectures, something that most people are already familiar with. In System Verilog, they're writing verification components in classes. In many ways, that's like throwing away all of the concurrency that's naturally in the language and switching to subprograms, but then augmenting those subprograms with the capability to fork and join.
Got it.
Okay.
Got it.
So if you love fork and join, you're going to love System Verilog. But if you like entities and architectures, you're going to hate it, and you're going to love OSVVM.
Yeah, I can see it's much closer to what designers do.
And really the original intent of the language. I would have been more impressed with what System Verilog did, is if they built on their existing structure and figured out a way, instead of doing software OO, a way to create a hardware abstraction layer for OO.
Right. Okay. What is OSVVM's status regarding IEEE approval?
We are an IEEE open source project. We're 100% IEEE 1076 compliant. There's a number of other VHDL methodologies out there. Some of them really haven't bothered with that. They have used features that were deprecated in 2000, 2002. So, yeah.
Okay. A question regarding the report slides, actually. Does OSVVM support requirements covering, or do you use a tool outside to do that, external tools?
We have some capability that allows us to interact with requirements tools. And that is a feature that's scheduled for updates. So if anybody is working with requirements now, I would welcome partnering with you to make sure the updates work with what you need to work with.
Yeah, I think requirements tracing is becoming a lot more into the safety.
Yeah, well, that's VHDL's market now, isn't it?
Yeah, and that's why I was thinking. Yeah, it's very much into the VHDL world, so it may be a.
Yeah, well, that's VHDL's mantra, is write code that works, and if it doesn't, then have the compiler pick on you a lot.
Yeah. And one last question is probably a very good one to end on, actually. How can I study and make a deep understanding about OSVVM?
Right. So a couple slides back, I gave you a page that starts with our HTML documentation, the osvvm.github.io. And I would start reading there, and then it references you. So I'd read that whole set of HTML pages and then go back and start with the framework and maybe and decide what you want to focus on first, right? If your focus is upgrading your current tests, maybe you want to study the alert log package and the verification utility library first. Because I find that was one of the things that was bothering me until I added to OSVVM was prior to having alert log, I was manually counting errors and I had all these separate error counters, and I had to scurry around my test and make sure I collected them all. And, at the end of the day, you're sitting down relaxing at night and you're like, oh, did I count this one? Well, with the OSVVM alert log package, it has a data structure internal to it. You recorded it against a data structure. It's going to report it when you call end of test reports. So that actually was a big relief for me. I didn't realize I even needed it until 2015. And then when I added it, I'm like, wow.
Okay. I think that's probably a really good place to finish. So a big thank you.
Oh, yes. Thank
Jim.
you for having me here. I really appreciate it.